course, with sari, you have to keep holding this. It's on? I think it works, right? You know, I'm sometimes clumsy with things. If I pull something, the whole thing comes off. All right, so what I thought was, I'll try and tell you why we should study this and then go on to techniques. You know, first let me tell you that I work more on the techniques and instrumentation, but I'll try my best to also, you know, try and convince myself also why we should do all these efforts. So that's a nice picture. And can anybody, does anybody know where this was? And yeah, of course, moon, but from where, and it's a very famous photograph, of course, with the moon rise from Apollo, just GK, but yeah, just asking you just to make you, you know, answer. When which mission was this? Which was the first orbiter that went to the moon, which really went around? Oh no, oh, I would be proud if it's Chandrayaan. No. Okay, you are 90s kids, but there were 70s when 90s, 2000, sorry. Yeah. 2000 kids, sorry. Even 90s is, see, I'm so old, like 90s is young for me, but yeah, there were times where, when did the first, when was the first lunar? At least the age was, like, when did Neil Armstrong land on the moon? All right, so before that they went, right? They didn't just send Neil Armstrong first and get out of it, right? They did try many. Apollo 11 was Neil Armstrong. So there are many Apollos before it, right? So this was Apollo 8. That's a movie playing, but just talking. So you can see really the Earth rise. Okay, this is sort of simulated from all the images. Not that they just saw this so clear, but this is taken from the module of Apollo 8. With 3 astronauts going around the moon. All right. So the best reason why we want to do planetary science is that we live on a planet, right? So what we want to know is very fundamental questions, very broad but profound. How did the solar system form? Because we live in a solar system. How do the planets form? Because we live on the planet. How did life originate? Very profound question. It's a big question mark still. And what will our future be, isn't it? Like, is it going to be always like this? Is Earth going to be always like this? No, right? We know this, it's a evolving time. This is just a point of time in the universe when we are here, we are on Earth, Earth is habitable. But if you look around in the universe, everything is evolving, changing, and it's just a tiny point of time. So here at this moment, what we just want to know, look at us, right? Tiny human beings, but at a point of time, but we have very big questions in front of us. To put it in more philosophical terms, it would be, who are we? Where are we? What will happen to us? And are we alone in the universe? So how do we start looking at such things, right? First is, okay, you can first maybe like, you can start building a theory and then see whether this match observations, or you can go the other way. Like, you can look around you, what are the clues, and then go and build a theory, right? So in the case of solar system, and like in many other cases, it's more from observations. So when we want to build a theory, or let's say hypothesis on how the solar system originated, what we should first is to really look and see on what basis should we start. Right? So what are the things that we can see? Planets go around the sun in the same direction, like all the planets are going around in the same direction, and the sun also rotates in the counterclock direction, which sort of tells you that if something started, they all began in a similar configuration. Like the star is spinning, and around it, when the planets formed, they were also in that kind of environment where they ended up going around the sun, right? It's not just that sun got these planets from somewhere else and put it around it, right? It all formed at the same place. Orbital planes lie close to the ecliptic plane. They are not haphazard, like I think most of them are very less, like a few degrees maximum. I mean, except for Pluto, all of them are in the plane itself. Again, it points to formation, co-formation. Circular orbits, again, which again tells you sort of age, because very early when something is forming, you can have eccentric orbits, but with time, it settles down into a very well-defined orbit. So all of the orbits of the planets have very low eccentricities. Planets rotate in the counterclockwise direction, which is prograde motion, which means, you know, right, like they go around and they also rotate on their axis in the same direction. Again, you can imagine that if you give a push, all of them do the same thing, except for Venus, okay, and Uranus. So Uranus is almost like something hit it and it's looking at you. Okay, let's treat them as special cases and at the moment ignore them and say they need special, they are just special cases. The inner planets are rocky and the outer planets are gaseous. Again, this points to some very systematic formation, and it's sort of imaginable that because the star is very hot, the planets that formed in the inner solar system should be made of refractory elements with high melting points. But as you go farther away from the star, where the solar nebula should be cooler, you can have planets with gaseous envelopes. So, our current very general understanding is the nebular hypothesis, where just as I said, as the solar nebula started forming, so initially I guess you know star formation, right? Like how does the stars form? How do the stars form? Yeah, somebody tell me, how do the stars form? Did you have a lecture or have you read? Yes. Yeah, so come on. Yes. Yeah, and what happens? Self-gravity, they come together, but they need a trigger. Sometimes we assume maybe it's a supernova explosion or right? Yeah, also gives it a trigger too. And there are evidences, in fact. I mean, we find nuclides that should have been formed in supernovae in the solar system. Well, that happened. So there is a central star forming, and around it there is gas and dust, and it is in these gas and dust that the planets form. If you call this a frost line beyond which ices would be formed, inside is where the temperature is hotter, you have condensation of more silicate materials, which leads to the rocky planets, and then you go out, you have icy worlds like Uranus, Neptune, and beyond that Pluto, etc. So hydrogen compounds, all of them can only condense beyond it. So again, that's just a pretty simulation, but so this is basically what happens. There is the star, and why is it expanding? Why is it going out? Because there is wind from the star when it's very young, and when as it rotates, it pushes, when the wind also pushes the material out. There's a pressure gradient here, so as you go towards the edge, it gets thinner. There is angular momentum transfer from the star to the disk that's coming around it. I mean, this is a real simulation, not an artist impression, I mean, putting into computer codes. NASA has this, you might have seen already, but it's a very nice data visualization studio. Now, if the story is right, this is a very common thing because you have so many stars in the universe, and you should see protoplanetary disks if you look around, right? That's what gives us confidence that this is happening. You can't just have only our solar system forming this way, isn't it? So when you look around, we do see, and so that's very good for our theory. You can see ALMA here, and you see these rings. This is from VLT. These were both on radio, and you can see very spiral. This is obscured. The central part is obscured so that you see these better. And that's from JWST, another edge-on view of protoplanetary disk. So it looks like we are in the right direction, right? And several of those ALMA images show that many have different shapes. Some are in the process of forming. Somehow, like these have very distinct rings, whereas some are more spread out. So very broadly, maybe you can think of this as just a sequence in time, right? Like when you want to put it all under a broader envelope, you can say, just like when you do galaxy classification, you sometimes say it's just it's a question of time that some of these might actually become rings later on. So that's all going fine. This is actually imaging with a coronagraph, so here again obscured, and you can see the planet moving in its orbit around it. In this planet forming, and there is a disk here, so you can see it actually happening. No, all that's fine. Then what is there? Like everything is done, you know it. So what is that now you have to do about this, right? So like Calvin says, it's only when you get into details you have a problem, right? So as you know more, you get into difficulties. I cut out the last part of it. If you have read this cartoon, he says, so you take action, something more is there, but yeah. So why is it still a hypothesis? I've just put some of the points which drive these kind of theories. First is the angular momentum in the system. So it started off spinning, yes, but today when you see the 99% of the mass in the solar system is on the sun, but most of the angular momentum, I think similar range like 95-99% is in the planets. So there is a transfer of angular momentum from the central star to the planets around it. How does that happen? Okay. So any simulation which is done should finally result in this angular momentum transfer. Enough matter in the disk. So as the star starts to form, in a young star there is a lot of wind which blows away the material around it. This happens quite fast because we can see other star forming regions how it happens. So this seems to all happen very quickly. Is there enough matter in that disk and enough time so that you can form such planets around it, particularly giant planets, right? So it looks like this all has to happen very quickly, right? So that's a constraint. You don't have all the time to do this. Explaining Venus-Uranus rotations, but maybe you can say it happened later, that some impactor kicked it and that's why, etc. That's what we say for Venus. Like it was rotating like this, but some impact happened that it just turned the other way. Volatiles in the inner solar system. So from our earlier condensation sequence that we talked about, looks like you can't form water in the inner solar system, is it not? Because the temperatures are so high, all volatiles including water has to condense away. They cannot come, but then very obviously, yeah, you're drinking water. So this is something that we take for granted, isn't it? Where did this water come from, right? Earth shouldn't have had this water. So of course we invoke later on comets delivered water, but there are many difficulties with all these explanations. So today I think we are rethinking whether the condensation sequence is right, and maybe it did from the beginning itself have some water. I'll not go into it, but that's a very important constraint that we have when you look at the temperature and pressure at those times. And even on the moon, which we originally thought was very dry and don't have water, today we have clues that probably in the some of the rocks that's come from deeper inside the moon, they do seem to have some amount of water. So and the formation time scales, as I said, for all this to form, this has to all happen very quickly. So how do you do that? And another important question that came maybe in the recent times is that when you make a theory for our solar system, it should cater to all solar systems, which then really is a big problem, because now you know of almost 6,000 planets around other stars, multiple protoplanetary disks. So all the solar systems, then can we have a single model, at least a general model that explains it? Otherwise we have to say this is an exception, right, like where we are. A big constraint or like observational constraint that guides this simulations and theory are the meteorites. We'll talk more about techniques of how we do this tomorrow, but just wanted to flash it that all that what we said in the earlier slide seems like it should have all have happened by about 10 mega years. So that's a very short time scale. How old is the solar system? How old is the solar system? like 4.65 something, which is as old as the sun. So not much difference. How do we know this?
Some like rocks and like some geologist has predicted date and the rocks.
Not predicted, actually, yeah, I know, right. And even for the sun, that's how we know, right? Like how do we actually know otherwise how old is the sun? Of course, you can look at stars and generally see that G-type stars like this, their evolutionary time scales. Yeah, you have a question?
Like there was this thing which was flashing like water on Earth dated more than our solar system is.
Water on
Water dated much older than
oh, okay. There was a recent news. Oh, I didn't read that. Okay. How can that be? Okay.
That's why I asked, is that true, like, or this is just
Water, I don't think you can date, right? Like it's more isotopic ratios that you do, not of water. D by H, which is the water isotopic ratio, it is more used to say did we lose water or do you have the original water. So you can assume that the solar nebula had a certain composition and then look at all the meteorites and planets and say in comparison to that what has changed, and then invoke processes to say why that happened, right. So that's how you go about it. So since this is a big constraint, just wanted to highlight that point. You see the time scale. So all this has to happen within this time scale, I mean formation of planets and all the small bodies. How do we know this? The oldest material in the solar system are these calcium aluminum refractory inclusions. So just to show you here, I think the largest of this is about 2 centimeter. So these are tiny pieces, like this part of it is the CAI, this part of it. Dating that, you get this number, which is how we date the solar system itself. These are not very common, so you're lucky you find this in a meteorite. So these, for example, here with the uranium lead isotopic ratio, you date them and say this is as old as this, right. So this is the first forming solids in the solar nebula, all right. And chondrules are small solids which we think is like local melting in the solar nebula. So you have density concentrations and they become small solids. Those are the chondrules. Again, they are also dated and looks like they span this whole timeline. Whereas you can see the CAIs are very narrow in their formation time scales. These are the iron meteorites. So meteorites fall all the time onto Earth, right? And sometimes you are lucky to find them. You can again, when you have something in the lab, you can do precise dating, and so it looks like they formed here. So Mars accretion should have happened. Again, here these are from the meteorites, but we do not have samples from the Mars. So looking at orbital data from the Mars and then comparing it to the meteorites that we have, some of them we believe are from Mars, so in that indirect way. And the growth of Jupiter's core should have happened here. This is the entire Jovian system should have formed by this time, and Saturn by this time. So aluminum 26 is a radioisotope. Again, that provides heating. Again, it's a short-lived radioactive isotope. So measuring that gives you the time scales in which the melting and the solidification should have happened. So forget the details, but what I wanted to stress again is the fact that very important fact is the timeline, because we know from real analysis in the lab that these all should have happened in a very short time scale, right? So you can.
So these and this aluminum and lead, all those fall from Earth that they are born in.
Yes. So these are meteorites.
How do you extrapolate to Jupiter and Saturn?
Okay. Okay. So that's a kind of, yeah, I mean in this case for the Jupiter and Earth we don't have meteorites, right? So these are from observations of its atmosphere. Only here it is from the Earth.
So
Observing. Of course a lot of modeling happens. Yeah, I understand. When you don't have anything from the Jupiter as such. Yeah.
Curiosity, I have a doubt, like we have dust called silica when the protoplanetary disk was formed. Have you ever seen a glass particle out of it?
Glass.
Glass in the solar system or anywhere?
From moon we have a lot of glass.
Oh.
Yeah. But that is thought to be not the original solar nebula part of it, but like glass. How does glass form? It has to cool very fast, right? No time to form the grains. So on moon there's volcanism. So something that's let's say magma came out from fissures and cool very deeply when it, so you form glasses. So it's a result of volcanism. Volcanism on the moon is different again, not like volcanism on Earth. It's more impact related, right? Because impacts come and liquidify the surface and so like that. So yeah, glasses are there, but more because of melting and cooling. So again, very broadly now looked at the solar system formation. Now individual planets, how do they form? Because we have to all these have to account for all the planets that we see, right? The inner as the and as well as the outer planets. So as we said, this is a cross section of how the again it's all models, but yeah, how the temperatures were here, and so at what points would metals and rocks form, ice forms, and beyond that methane and like where the Pluto and the Kuiper belt objects are. So what we believe happened is like this. Initially in the nebula, in the protoplanetary disk, there is dust and gas. So if the dust gas ratio, again there are numbers for this, like dust gas ratio should be higher, and you have small dust particles which stick together and grow in size to form a small core here. In simulations, at least up to a few centimeter size, looks like it's possible to grow them. But one of the yeah, so but initially, so they have very small gravity. So it's just that the density is so high and they are moving around. It could be just they come in touch with each other, just like if fine grains. We are talking about micron size grains, right? If you clump them together, they easily clump. It's difficult after a point. So it's easy to clump together very small grains. You're talking about that size because surface area, surface contact is high, and they are moving in this gas and dust. So now imagine they are in orbits around the sun, and as they grow together, they clump, and here and there you start forming these core particles. And after that, these small cores grow again by maybe collisions. They stick together and start growing, like and beyond a point, what we call critical mass, they can also accrete gas because they have enough gravity to bind the gas to it. So they start binding the gas, and beyond what is called a critical mass, there is a runaway gas accretion, and you form the giant planets. So that's a very broad way in which planets can form, but this is what we believe happened. But then there are many, most of this is with simulations, right? And then you have to because after this critical mass, it just keeps growing. And so again, how big can it grow depends on, is there still gas around? So this has to happen very quickly. Now by the time it reaches, like looks like in our solar system there are no bigger planets than Jupiter. By the time Jupiter got all that gas, the other things have been swept away. So it didn't grow. But you know, in many other exoplanets there are much bigger planets. Probably they formed slower. So time scales here matter. But some of the problems here, like why there are different simulations happen, even you can see very latest papers also with simulations, because many problems in this, there are many a variety of parameters here. For example, viscosity in the disk, the pressure gradients, and it's not just Keplerian orbits, right? There is drag, right? So if you want to trace how a particle is moving and will it collide with something, and look at individual particles. So in a simulation, that's how you would go, right? You need to consider the viscosity of the material, the pressure there, right? Not just a Keplerian orbit. So you have a lot of free parameters to play with here, and most often therefore you get multiple you don't converge into a single solution. And at the end of it, what are we looking for? Can all this give us planets that we see, the rocky and the gaseous planets? As I said, some of the problems are these, like from here to here, how does this core, because as I said, it's easier to put together smaller grains, but beyond a few centimeter, if they have to grow into meter size, which we call planetesimals, how do you do that? So, okay, things are invoked, like locally there is a pressure bump, and which allows all the material to just fall in. So, there are many ways you can do that, but you know, which is the right thing, we don't know yet. And scattering, because we said this is a very chaotic place, right? There are lots of such small pebbles going around, and you can imagine they're all impacting each other, which means they'll undergo scattering. And another thing is that when they scatter, very likely that they can be pushed inward, and if you're closer to the star, everything will go into the star, right? And because of the drag, their orbits also decay. So you know, you can imagine how all these parameters has to be then so much fine-tuned that you get what you see today.
So like the brown dwarfs and fade, like Jupiter and stuff also from
Yes,
fade stars.
Jupiter, brown dwarfs. Yeah, yeah. When we believe brown dwarfs are like.
So we call them fade stars just because of the large mass, nothing.
Right, right, right. It is just above what we would call a planet, that's all, yeah. But otherwise it's not luminous and all that. Yeah. And planetary migration. So, when the mass goes higher, you can't stay in the same orbit, right? Then you will move. So, there is planetary migration. So, then what happens? If you move Jupiter inward, will other orbits stay the same? No, right? So, then everything is upset. So, imagine lot of such small planetesimals going around in that disk, the wind from the sun, the drag there, and as they grow, they are all moving in and out. You can imagine how bad the situation is, right? So, yeah, so all these factors have to be taken into account, and I just put one of these latest models where with simulations using such a theory, they can reproduce a gas giant, ice giant, and a terrestrial planet. This is the core formation by solid accretion, gas accretion, and it slows down now. If it slows down, because the gas has been swept away, then it becomes this, and if there is no gas left, or it didn't go beyond, because now Earth is like in the inner region, so by the time it's forming this solid part of it, the gas has probably gone away, so it can't. So, for the inner planets, the atmosphere that we have are secondary atmospheres, right? Whereas for Jupiter, we believe it's, I mean, for the gaseous planets, a lot of the primordial atmosphere is still there, but for us, we don't have our primordial original atmosphere. Like even if it had accreted gas, all that has gone. What we see today is just outgassing from the planet. So, you can compare the atmosphere of Jupiter to solar photospheric abundances and see, you know, does it match with the original solar nebula. This is another paper where they have done simulation, but just want to show you here that they have to really fine tune to get this particular option of our Venus and Earth, which are similar in size, but you have a small Mercury and Mars is small. So, again, one of the problems in all these is getting the size of Mercury and Mars right, because these are all very close by. You ideally would like Mars to be as big as, I mean, in terms of how we are driving this theory. It looks like Mars should have been bigger, but then we have a small Mars. So, getting there requires a lot of fine tuning. So, in Grand TAC model where the disk is very narrow. So, again that is another thing, like you get to get this at the right position, if the disk is really spread out, I mean it is a wide disk, you have lot of small, you know, you have lot of things to accrete onto that planet. But if you assume a very narrow region where only from which you can accrete, then you can't grow beyond a size. But Mars is near an asteroid belt, so it should have had more things to feed onto, right? But then it's not. So, I mean, that's a problem that you have to address. Since I mean, we talked about planets, but you have other things in the solar system like the asteroids. And you can see they're all are very different shapes. I'll not put the names, but this is Itokawa, and maybe you all, I don't know how many of you follow such things, but it's just fascinating to know. Itokawa is a mission that JAXA went to and collected samples. Okay. Yeah, Hayabusa. This is, I think, Bennu. Yeah, is Osiris Rex, which is a NASA mission, brought samples to Earth. You can see the shapes, how different. This is more like a rhombus. This is kind of no shape, and this is somewhat bone shaped. I think this is more of a reproduction, but yeah, these are real photos. So basically to say that they are not round objects, right, like planets. So you can imagine that they did not really form like, or they are probably just leftover planetesimals which didn't grow into planets. So to become a sphere, you need to have a minimum mass. The largest asteroid is Sirius, which is really circular, but we just still call it an asteroid. Another reason why they are asteroids is because it hasn't differentiated. Earth is differentiated into crust, mantle and core, and so are other planets, whereas asteroids we believe are more, they don't have such a differentiation. I'll come to how we differentiate later. So some of them like this are thought to be just a rubble pile, like many of held together, loosely bound by some gravity. Okay. It just happened to be. That's why they are irregular as well. They spin also. So all that again tells you how they. Now asteroids are important also because you all the time hear an asteroid is going to hit us, right? So following their trajectory and how fast they are coming in, how big they are all important for our own safety. In next one, near Earth one, was talked about I think in 2029, April 13, Friday. There's one that's supposed to come. Yeah. It's not just the main belt. We have a lot of asteroids in our solar system. You can see named as Trojans, Earth Trojans, and Jupiter Trojans. So there are these resonance just because of orbital dynamics where you can find these asteroids. But if you just take the main asteroid belt where most of them are, again you can see patterns. The total mass in the asteroid belt is only like 1 × 10⁻⁴ of Earth, which is very low. The eccentricities are again in a narrow range, but you can say the orbital inclinations are higher, some go a little above the plane, and you also see a pattern that compositionally the inner asteroid belt are something called S-type asteroids, and as you go outer you have C-type and D-type asteroids. The type has been defined mainly by spectral reflectance, like how does their spectrum look like. So they are more, you have to evoke different way of formation for basically formation in the sense where did they form in the solar system. So what does composition really tell you? Like if you find rocky silicate without volatiles, you think that that's inner. If you find icy things more volatile rich, they must be outside. But this assumption is being debated a lot now because our looks like our initial assumption that everything just evaporated away may not be really right. And there is a mission thing going to Jupiter, Trojans. Yeah, I think it's on its way. Lucy, there is a mission called Lucy, which is going there kind of. Yeah. Okay. Very early on there was this thought that there should have been a planet over there and it just couldn't form, and that's what it is. Basically looks like there is a concentration there. I mean this is according to how it should be in orbital dynamics wise, but it's not a planet, it just spread out. So these are indeed leftover from planet formation, and that orbit is ideal location in terms of dynamics, but yeah, why it is a belt is not very well known.
Like as you said, Mars should have been a bit bigger.
Yes,
than
yes.
Is it could be because Mars, like due to some mechanism, could not accumulate these and
Yeah.
they just became a
Smaller.
spread out belt. Is it could be because of that?
Yeah, that's what Mars could not get these things onto it. But again, why? Like, is it about time scale or? And Mercury is also much smaller like this. So Mercury is also a problem. But sometimes.
Is it could be because Jupiter is like so heavy and because of its gravitational pull, it kind of didn't allow Mars to get.
Yeah, it could have come inward and then pushed Mars, etc. etc. Yes, that's where migration is.
Apparently, like Mars was big and there was some collision of
Yeah, well, that's the easiest. You know, like that way scientists are very clever. Like it's easy to make a story, right? But only problem in planetary science and astronomy or like in other I think, I mean, not really know this, but in astronomy there are points of light. Beyond a point, you cannot resolve or bring something onto the lab to analyze it with great detail. But in planetary science, the thing is you can go there, you know, you can walk around row, so you can't just make a story as much as in astronomy, right? There are more details here.
Despite the high density of these asteroids, why do only a few of them impact with Earth? Is there
With Earth. Oh, currently because thankfully it's all settled in, yeah, I mean there is a pull from Jupiter as well, and the dynamics are such that you don't want it to, right? I mean it's sort of settled in these orbits. But that's why near Earth asteroids, it's all about how gravitationally bound they are to their, where they are.
also launched a DART mission? Like
DART mission, yes.
And like in few million years, sun would turn into a giant.
Yes, white dwarf,
Yeah.
first
So
time.
that
Red giant first time, yeah.
could there be a planetary formation after that? Like
No, you don't have a source, I mean, okay, planetary formation requires material basically,
yeah,
right?
like gravitation disruption could
Push things out, it could push things out. If there, okay, you have to see like if there is enough material, I mean, if you're saying that everything is pushed to a corner, maybe, yeah, possibly could, yes. Yeah, so yeah, NEAs are always a threat, even to space platforms, right? Like, I mean, not only asteroids, the micrometeorites. Like, I didn't mention that, but if you just go into space, there are micron size meteorites which all the time hit. So if you are in a low Earth orbit platform, you also have to safeguard your spacecraft, or when humans go, you have to be worry about these meteorites puncturing, because they come at very high speed, like 8 km per second to several tens of kilometer per second, quite high speed. And yeah, we'll talk about that. I'll digress. And there are comets. So I don't want to, you know, it'll get into more information if you start discussing how each of these formed. But just to mention, there are comets, and these are, so you know, okay, I've already written, but have you been to Hanley, anyone? You should go, okay? It's one of the best observatories we have, right? And you can see the comet here passing by, and actually you can see the Milky Way from there, like enough exposure. And that's a comet, again from the telescope taken by Arvind and Shashi at PRL. You can see the comet passing by here. Now comets, I think more familiar because we actually see them sky, we discuss about them. So there is a coma and a tail, and as you go towards the sun, that's why the coma comes, etc. But basically they are like asteroids, like the core is rocky. This is a picture from, there was a European mission that landed on a comet, right? Yeah, Rosetta, yeah, on Philae, yeah. Nice names, right? You should all propose nice names for our missions, not Chandrayaan 1, Chandrayaan 2, Chandrayaan 3, right? We have Chandrayaan 13, 14 going on, so you could better propose nice names, right, like this. So basically they are also rocky objects, but comet seems to have more water ice inside. So that's the reason we think comets delivered water to the inner solar system, because you also see them coming some at regular intervals, and and they must have formed in the outer part of the solar system because they are icy, and you know, due to some orbital trigger they would come inward, and then that's how we got all the water from. It was the theory, but as I said, it's not so very true at times. Maybe some we got, but again, what did I have? Yeah, so I just wanted to you know, a little bit go into moon as well, because I basically work on the moon, so I can't leave you without telling more about the moon. And also moon is the body which we know most about. Right? Most missions have been to the moon. We have samples from the moon. We have people who have walked on the moon. So, you know, the best body, and it's accessible. It's just a 5-day journey, right? No, no, you see in the Chinese are planning 2030 to have humans on the moon. Okay, Artemis we have to wait and see. Okay, we also have a plan to have humans on the moon. Could be one of you, right? But or at least maybe 25 years from now, let's say. I'm sure there will be you know, tickets to the moon. Right? So yeah, you better know more about the moon than any other body, because it's not just scientific interest. There is a lot of economic and you know, that kind of interest to go there and have habitats, etc. So Venus and Earth, these are the inner planets. Sorry about leaving Mercury, because Mercury is very close, and you know, there's been many things about Mercury unknown, but you know, I didn't want to go into detail of every planet, and so it's more to give you a you know, overview idea of planetary science. So Venus and Earth are very similar. So Venus is called Earth's evil twin. Yeah, for Venus it's not evil, just that it's very toxic atmosphere there. So that's why. But it's very geochemically similar, whereas Mars is very different. And another thing about our moon is that it's very special, because only we have a satellite, and for a satellite it's too big. If you look at the satellites of Saturn and Jupiter, it's like 1/100th of its size. So you can think of like in the same way how satellite planets formed around the sun. You can say there was leftover material from forming Jupiter. There was some dust around it, and those satellites just formed there as clumps. But for moon, that's difficult to say, because moon is too big to do that. You have to. This is almost like 1/4 the size. So to form moon around Earth in the same way, it can't be like that. So you need some special theory to account for the moon. So it's a very you know, because we can't do the our normal thing that it formed as a accretion around the moon. We invoke a special case for Earth moon, where Earth had just formed, and then a big impactor came. It's called Theia. We also named it, which is the size of Mars, and yeah, it hit, and that's called the giant impact, and that's how we have the moon. We also see moons around giant planets form in circumplanetary disk. That's a first deduction, I think in 21 using ALMA. You can see around a giant planet how a moon is forming from our old way of forming, like in that dust around it. So let's say all the satellites of Jupiter, Saturn formed in that way, so you don't have to have special cases for them, but for our moon it's special. So one of the hunts now is also to look for exomoons. I mean, are these really common? Because in our solar system, if it's so special, do you also have to, I mean, every solar system, if you find a moon like this, you have to say, okay, that was an impact probably, or like, right, then it becomes common. So are they really common? So it looks like it critically depends on the vapor mass fraction in the impact event. So even if you have impact, of course every planet must have had impacts, because we said it's so chaotic as they are growing, like a lot of things going around, planets are moving in and out, there has to be impacts. And in fact, we have evidences if you look at the moon surface, for example. There's so much cratering that's happened on the moon. Moon is like, it's recorded all those events from 4.56 billion years ago. Whereas all the inner planets must have also suffered this, right? It can't be that everything goes and hits only the moon. Everyone is hit. But just that Earth doesn't have that memory, because things have changed on Earth. Same thing with Venus, same thing with Mars does have some impact cratering, but not so much as the moon. So we take moon as the point of reference to really see all the events that has happened in the solar system. That's also one reason why moon is so important, because nothing much has changed on the surface. So if you look at the moon, it's like it's telling you from 4.56 what happened until now, right? That's really nice, right? There's a record there. So if you look at that, we find that there's been an era of heavy bombardment as well in the solar system. Apart from that, okay, from the point of view of the formation itself, every impact event doesn't make a moon. If so, all of the other satellites also should have got one. Looks like in simulations looks like the vapor mass fraction, because the impact creates a lot of heat. So, something is vaporized. The mass fraction of that in the impact event is what decides whether you are going to have a moon or not. And also this forms beyond the Roche lobe, right? Like Earth's, I think it comes around beyond 2.5 or so, I do not remember the number exactly, but around that. So, all that material, now the impact happened close through our material, but only that material which is beyond Earth's Roche lobe really accretes, right. So, there you have to have enough mass to put these together. So, a lower VMF. It's like it's very, I mean, because we know the age of the moon from rock, it's happened like when it's 100 mega. It's like probably Earth hasn't formed fully. It's like proto-Earth. Yeah, you know, I think I don't remember early moon formation models. I don't remember who said this. Darwin. Anyway, so it was thought that the Pacific Ocean is the place where the moon is torn off. Okay, so the very early on theories about this was that something hit and a part of Earth is thrown off, but really people believe that the Pacific Ocean is that part of it, because it's a deep part. No? Yeah, so, but you know, if you imagine Earth can't take such a big impact, when it would have gone into pieces if it was a solid thing hit, right. So, you invoke that maybe it was partially liquid so that it can take that impact. It's even otherwise rotating, but that momentum transfer would have made it spin. So, I think the number is 4 hours as of now, like with that impact it's 4 hours is the speed, and then now it's 24 because there is an angular momentum. Now this angular momentum of the Earth-Moon system is conserved, and Moon is moving farther away and Earth is slowing down. So, 24 hours is also only at this point of time, right. As the Moon is going farther away, what happens? Our days are getting longer. So, you can be in the class longer. So, this is a nice paper where they use simulations to see what is the zone in which really such you know, large moons can form, and looks like even if such impacts happen, it's only a particular mass of the planet that will lead to formation of such big satellites. Even Pluto and Charon is another example. Even though it's far away, it's also a relatively you know, bigger size satellite. Pluto's. What is SPH stand for? What is this? Oh, single particle hydrodynamics simulation. Yeah, so these are more dynamic. So when you do the simulation, really you are following the trajectory of the particle, the angles, right. So you can also try doing that with a toy model. Take 2 particles, start putting them together and see what are the influence on that, right, and see how their trajectory would be. So, okay, because we started late, is it like we go by? If you are feeling like enough, let me know. Don't feel any, I mean, I'm fine if you want to stop also, okay, just tell me. Otherwise, we'll go a little bit more. Okay. So, the key constraints again, just like we talked about the constraints for solar system formation, here also there are certain constraints which define how this giant impact model could have happened. Again, the angular momentum of the Earth-Moon system, how the, you have to start with, like we see something today. So, you can only bring the moon as close as I said, 2 point some radius, right. So, after the impact, that's your initial starting point, and you should get to what we see today. The disk mass should be greater than the mass of the moon, isn't it. So, these are your initial constraint to start your simulation, and very importantly is the geochemical constraint. So, the giant impact theory though was talked about in the 1940s, a real theory developed after the Apollo astronauts brought back the samples, which showed indeed that looks like there was a melting event on the moon, and looking at how similar it is to. Now, in the whole theory, you can imagine like if it is like impact happened, and there should be some similarity to the composition of Earth and Moon. And also this impactor could not have come from the outer edge of the solar system and came and impacted. It has to be somewhere nearby. So it has to also be a rocky planet similar in composition. So these are our constraints. The constraints that we understand from the sample analysis is the volatile element depletion. So compared to Earth, Moon is depleted in volatiles. Okay, you look at any volatile, not just water, things like sodium, potassium. So its abundances are much lesser than water. So again, we try and say this is because its formation is such a catastrophic event, which generated a lot of heat. Therefore, it could not retain its volatiles compared to Earth. There is a low iron content on the Moon, bulk Moon, compared to Earth, because Earth's core has a lot of iron, and we even have iron. So bulk iron on Earth is 33, whereas on Moon it's like 7.58%. See, every time when you read these things, I should say you should also think how are they doing this, right? How do you go and measure the iron on the Moon, the whole Moon? So a very important point I want to say is when you read about these theories, and a very important thing is to what technique did they use, how did they come up with this? And always as I said, the devil is in the details. As you go deeper into it, you see there are lacunae in what I explained, and that is where you can identify your scientific problem of interest. So you should not just start off by thinking that everything is done, right? Copernicus, we thought before that, people thought for 400 years that Earth is the center, right? If you are in an era where something is really wrong about what we think, imagine. Huh?
We thought Earth was flat for some time.
Now you are laughing about, but something that you are now believing, somebody else might think of how stupid of them, right? So, what I mean to say is that you should always see how did they arrive at that. Right? So, bulk Moon, when you say 7.5, it's a mixture of getting those samples, extrapolating, and some understanding of with seismic measurements, how its interior is, how it's looking at its size and perturbations in gravity, etc., estimating with models that this could be the bulk iron. Right? So, always when it comes to models, there are assumptions, and as you get more and more observations, you get to improve upon that. Otherwise, we will stop our lunar science, right? What is there to do? You got many samples. This is a question we will all get. The Chandrayaan 4, we have a mission to bring back samples. Why do you need it? You have like almost 400 kilograms bought in the 70s, and is there something that you still can't answer that you need to go now and get some? Right? You need to answer that, right? So silicate portion of the Moon has a higher iron oxide, higher than on the Earth. Just details, but both are silicates. In fact, the major elemental abundances of all the inner planets are the same. So when I say major element, what we mean is all elements which are more than 1 weight percentage. We talk about it in terms of weight percentage. So percentage is like, if I assume I know all the elements in it and it's 100, if I say 7 weight percentage of iron, so it is, initial assumption is I know all the elements, and out of that 7% is iron. All right. So all inner planets are silicates, Si2O4, and you have elements like magnesium, aluminum, silicon, calcium, titanium, iron, which are the major elements. Oxygen, right? Because oxides, many of the rocks and minerals are oxides. All that has a on the Moon, that silicate portion of it has a higher iron content than that of the Earth, right? So what I mean to say is that although the bulk is low, the silicate part of it seem to have higher iron. So you have to explain all this finally when you make the giant impact theory. Isotopic composition is similar to Earth. Now, isotopic composition is very important because it's very sensitive to processes that can change, for example, D by H is a deuterium to hydrogen ratio. Initially, let's say in the solar nebula you have certain D and certain H. Now, if there was heating, because D is heavier, you will preferentially lose more H. Then your D by H ratio decreases, right. So, like that in any isotopic ratio, if there is a change in this ratio with time, that means it is because of certain process that is happening. It happens so in that in our solar system, isotopic ratios, especially of things like oxygen, are very sensitive to where they are. So, if you draw a line from the sun to the outer solar system, at every point you can say this should be the oxygen isotopic ratios. So, that puts a very heavy constraint on where moon formed and what is the composition of the impactor, because impactor then is somewhere nearby. Right? It seems to be like the first thing itself, like similar composition of Earth and Moon and Earth are not very different in composition, means that when the impactor, if some impactor material has gone into the moon, that's also seemed to be similar, not that it's completely different. So, we take it very conveniently, whatever differences are there, we blame it on the impactor, whatever similarities are there, it's because there is Earth material, right. So, lunar geochemical data remains the best bet to constrain our model. So, bringing back samples was so important to understand about our own Earth, like did this impact happen, when did it happen. See, in the larger context of say habitability, right, big search is to see life. So, such impacts, if it happens now, that is it, right. You know about the when there is this thinking that the dinosaurs disappeared because a big asteroid hit, right. So, something like that happens, that is the end of humanity, right. So, such kind of impacts, I mean it's nature, are very important thing to constrain. And what happened in our solar system. So, if you look at extrasolar systems, you should also know at what time scales all this settle down, there are no more impacts, and it is on those systems that you can look for habitability, right. So, having a moon, I mean having an impact generated satellite and still having life constrains the time scale of habitability in our planet. And also in fact we say that because of the moon that biology itself gets affected. I mean in the sense, see Earth's day and night cycle changes, right, with time in geological time scales of course, but it is all driven by moon being there, right. And it is also said that because of the tides that aquatic animals, maybe it influenced them coming onto Earth, which means evolution of life also has something to do. And if you look at I don't know if you know, a reproductive cycle is connected to the moons. I mean why should it be, right, 28 days. I mean it is not in just humans, in fishes and many such animals, the reproductive 28-day cycle is to do with the lunar cycle. Okay, I don't know, I mean I don't know much about this connection, but it is not really a coincidence, I guess. Anyway, so just want to again iterate that moon is very important, and you better find out how moon came about, because it is very closely connected to Earth. The giant impact has problems. It is not that we finally know how it happened. The canonical model is like this, that the impactor came and formed a disk, and there was a lot of vapor and everything coalesced into the moon. Low energy oblique impact, but it looks like this has to be a very fine tuned small scenario. Like this happens only if it is a low energy oblique impact and a very narrow range of angles. Difficulty in explaining isotopic composition of the birth moon, because absolutely the impactor signature does not seem to be there on the moon. Other scenarios also can form the same thing: high energy impact, multiple impacts, impact on a magma ocean dominated proto-earth. So, for now I will say just means that it did not Earth has not yet solidified, it was still in that process when this hit happened, so that there is some mixing. See, if you on a solid body something hits, very less mixing, but if you invoke that actually there was some mixing, so that now you can't make out what impactor was originally, already this all mixed. Larger range of, in this scenario it is a larger range of possible impact scenarios. High energy delivered helps Earth and impactor material mixing, and it sort of explains the similarity. No, to our convenience we can fine tune this and say why are the differences there and what are they. And this is a recent paper where they invoked the same giant impact, but did not just form, I mean moon didn't form just like that, but it forms a kind of disk like this and so on. So again the question is just one moon, right? In this scenario we would have formed multiple moons. So either they were and they were not successful in being a moon.
This suggests that there should be an asteroid belt around earlier time.
Not asteroid belt, in the sense there was first, okay, moon formed very quickly in a few million years.
But it cannot, like the remaining part of the asteroids, it cannot, all of it cannot form in moon. Some has to be remaining.
Maybe it went away. So it's not really asteroid in the sense, because when we say asteroid we're talking about the primordial material. This is still material from Earth and the Theia.
We should have like rings like Saturn.
We don't have. So that's what formed the moon, right? And it's all swept away. Finally Earth also has to hold on to it. So before giant impact, another popular theory was capture. Like it can be that a rock planet was going around and just caught it. Can happen. But yeah, it's too big for that anyway. And moon is almost like a planet for all other, its evolution wise, because it has again a crust, mantle, core. So if an alien looks at us, they might classify this as a double planet rather than a moon and satellite, because moon is big and almost like a planet. So moon is also a good example to study terrestrial planet evolution. And as I said, you can see how the abundance. So in fact, all elements in the periodic table will be there in every planet. It's just about how sensitive our measurement is. So when you say something is made up of these elements, it doesn't mean that's the only thing. Like here you can see that many elements are written, even very high Z elements. And compared is Earth and moon with two scenarios. So this is a mantle of the Earth, okay? Because the impact, probably it's not just the crust of Earth, or it could be that Earth actually hasn't differentiated. So there's quite a mixing kind of, and you can see it's very close, right? Most of it is very close, except for these volatiles and the alkali elements, which again moderately volatile like sodium, potassium, and some of these high Z elements again very. But the thing is, the differences are what is interesting to fine tune your scenario of formation. Just 5 minutes, or I think I thought I'll just stop with this maybe, and then techniques will go tomorrow. So just not the moon, all planets had magma oceans. So for moon we call it LMO. It's again a hypothesis which says that after the impact, when the moon formed, it looks like this. It's like almost completely molten. Maybe there is a core, because for moon one of the uncertainties is we now think it has a core, but how big is it, we do not know. So there is a small metallic core. How do you measure inside of the Earth? How do you know what is inside the Earth? Seismic. You can't dig enough. No? Yeah. So it's seismic activity. Same thing on moon. You can keep seismometers. There's that activity. Moon has moonquakes, but it's much lower. Mars has Marsquakes. Only difference is that Earth has what is special thing? Another special thing other than us that Earth has. I said other than us. Water is there. When we think water was there in Mars also. Plate tectonics. Okay. Tectonics is there. The plate tectonics. Okay. The movement of crustal plates. When no other planet, this is a single plate crust planet, like moon. We have these plates, right? You have studied in your school geography that, what was it called, the big continent that was there originally? Pangaea. I forgot this is in the school. Yeah, Pangaea. Because it was like that. And how did they all move, right? See, if you look at the larger picture, all this contributes to evolution of life, right? And the diversity that we see. It's all very important. Each step Earth is not just doing this randomly, it means something. So that separation of landforms happened because of the plate tectonics, and that's why we have mountains the way we have it, because these faults come together and at the joint. Again, you have studied all this in your geography class. Yeah.
And then how does Mars has a moon? Like it's a mountain.
It's not a mountain like we say, it's more a shield volcanoes.
Okay. Because it's like even 3 times larger than.
Yes, yes. It's larger because the gravity is smaller and can grow. Right.
So earthquakes like movement of plate tectonics, is that earthquakes and
Yeah. So again, the crust can shrink and right. Internally there can be tectonics. Like
Moon doesn't shrink.
yes, actually moon you see evidences of shrinking. Mercury even more. So you can see those wrinkles on the moon. Not as bad as Earth, but it does. And even meteorites lead to quakes. Like meteorites fall, you hear it basically. So basically, if those shocks propagate and you measure it, as they call S waves and P waves, if you measure them, you can model how it is weakened and how it's dampened. Looking at the profile, you can say what material it's coming through. It's again a model based on assumptions. So like that we know moon has probably a very small core. So it was molten in the beginning. Again, this is what we think happened, and then as it's cooling, see after the impact it has to cool, right, because nothing is heating it anymore. So it has to slowly cool, radiative cooling, and as it cools, materials become solids. Now what will be the again the same way, those with high melting points will solidify first, right. So here olivine or such kind of minerals, they crystallize from this liquid magma because they are heavier, they sink and they form the mantle. So the crust will be of lighter material because the heavier ones sink. So what we see today is a bright crust which is made of rocks called anorthosite. It's nothing special, something that you see here every day, just that we call in geological jargon, you call it anorthositic, etc. But it's a rock type, but it's just some kind of rock, just that abundances will be different. When you look at the moon, you see this bright regions and right, with the naked eye you can see, right, the dark patches and the bright regions. Those bright regions are anorthositic rocks, and that's the crust of the planet. And this is how probably the cross section is. This is a very broad thing, and as you know, if you dig deeper, there are a lot of things that you still need to understand. So it's still a hypothesis. And then how did those dark regions come then? Like, so initially when moon formed, it's like full bright without those spotch marks. Later impacts seems to have formed large basins like excavated material, and the impact melted material caused fissures, and from deeper within the mantle things meaning magma came up and filled those basins. So if you look at the moon, you see those dark patches which are magma filled regions. If you look at the far side of the moon, you don't see much of them. Again, an open question, why is it one side different from the other? I think I will not go on. Maybe we will look at tomorrow. I thought tomorrow I will more emphasize on how we do all this, because that's what you have to do, right? Otherwise you would think that it's all done and you don't have anything to do in planetary studies. I don't want you to think that. So, okay. No need of clapping, it's a class. you clap your teachers. You do? Oh, daily. Okay. So this is because if I come tomorrow.